Hi, I'm Paco Nathan with O'Reilly Media, and today it's a great pleasure to get to speak here with a good friend, Pete Warden from Google. And what's your title these days, I should ask?
That's a good question. I think tech lead for mobile and embedded TensorFlow.
Oh, fantastic. Fantastic. You know, I've got to say that I think it's been maybe 5 years ago, you invited me up to lunch.
Oh, yeah.
Remember we were looking through the image recognition. That was probably the first time I'd ever seen a real deep learning app. For something useful, of course,
Yes.
I should qualify, but I mean something truly interesting with deep learning there. And then from there, TensorFlow and the rest emerged, basically. What's this thing?
So this is a microcontroller. I'm just going to hold it up here. And this is something you can get for under $2 from eBay individually. So I bought a box of 100 of them, which I now have cluttering up my living room. But what I really like about them is that they're actually pretty easy to program.
Interesting.
And having something that's really cheap and really low power and has a bunch of compute on it, I mean, it's kind of like the next level beyond the Raspberry Pi in terms of just having something you don't have to worry about. If I step on one of these, it will hurt my foot a little bit, but I can just pick up another one. So.
Do the cats pick them up and toy with them?
Yes, yeah, I had to do a reorganization of my tech corner, as it's called, because we discovered one of the cats had actually taken a jumper lead and was using it as a toy, which was we really don't want. We're like, our cats are dangerous enough without letting them get into electronics.
They're evolving.
Yes.
Wait, what's the name of a board like that, though?
So it's funny because this is actually a Chinese created board, and it doesn't have. We've seen various different names for these. Yeah, which is surprising, but they've come to be known as the Blue Pill boards.
Okay.
Yes. And they are actually clones. They're very, very similar to SD Microelectronics F103 chips. So they work exactly alike. I think I might have seen that they're actually licensed from ST. But because they're pretty much the cheapest microcontrollers you can buy individually.
Interesting. Okay.
They've become really popular with a whole bunch of hobbyists, and you can find all sorts of sort of websites about like programming these to do whatever you want to.
And for programming, do you stick a cable in and do it on your laptop, or?
Yeah, so you can do that. I've actually found it easier, and I have some resources on how to do this using a Raspberry Pi as the thing that you program it from.
Interesting.
So the Raspberry Pi is kind of the big daddy, and this is you use the GPIO ports, and you just plug in like 4 wires from the Raspberry Pi. You use the OpenOCD software that you can download. And yeah, I've got a whole bunch of instructions and some pretty diagrams for how to wire this up. It's at github.com/Google/STM32_bare BARE_lib LIB.
So Google on GitHub, and then STM32
bare lib. And I'm sure we'll figure out some way of getting the URL written down, because it's not the easiest.
There's almost a kind of continuous deployment process then going from the Raspberry Pi onto these boards.
Yes, and the other nice thing is that you can actually run software emulation of these too.
Oh.
So we do actually have, we have been doing, you can debug and test and run on your laptop without needing any actual physical hardware to hand. So there's a great project out there called Renode, RENODE, which lets you, you'll see some references to it in the STM32 bare lib project, where you can actually just run this without having any physical hardware at all, and just play around with it.
Oh, wonderful. And also, just to give some context here, what kind of applications are you doing with this?
So one of the things I'm really interested in doing is running machine learning models on this, which may sound like a crazy idea, but especially because, I don't know if I mentioned, but this only has 20 kilobytes of RAM.
Really?
And 64K of flash.
Wow. My USB stick probably has...
Yes. And you might ask, well, why you were looking at a chip that has that little storage?
Yeah.
Oh, the main thing is that chips like these are both very, very cheap. Like in industrial quantities, you can buy them for well below 50 cents each.
Oh, okay.
And they use very, very little power. Like you can run something like this on a coin battery for, weeks and hopefully months.
Oh.
So you're really liberated from having to, sort of charge or plug in. You can use it in all sorts of places because it's so cheap. You don't have to worry about
a little solar cell that catches an hour of light a day or something.
Exactly. Energy harvesting from just the lights in a room is totally possible. So it starts to open up all of these applications for doing compute completely off the grid. Like you don't need any network, you don't need any power, you just have little standalone magical devices that just kind of self-powered, and have sensors on them and can kind of hopefully make sense of the world around them.
Could they conceivably do any kind of mesh or networking, low power network amongst themselves?
They definitely could. I've actually been really focused on things that you can do without any network at all.
Okay, great.
Just because the power that's required to do any kind of radio, it seems like the rule of thumb is like the smaller distance you can move bits, the less power. So doing computation on this uses up almost no power. Doing arithmetic, doing math, uses up almost no power. If you have to fire up even a Bluetooth low energy or something like that, then you're suddenly into the double-digit milliwatts.
Right, yeah.
And then Wi-Fi can easily be hundreds of milliwatts. Right. And whereas doing compute on this can be single-digit milliwatts, which means you can do it for so much longer.
Oh, fantastic. Now, what types of machine learning have you been able to put onto a device like this?
So it's still very much a work in progress, but you really can take neural networks, just like the ones that we were playing around with 5 years ago to do image recognition, and do things like very simple voice recognition. So if you actually look at the modern phones that are out today, things like Siri and OK Google, and my phone usually goes off when whenever I say that. But they actually have very simple voice recognition models running locally on chips very much like this, so that the main CPU doesn't have to be powered up, so that they can actually spot when somebody says something. Running on this very, very low power chip that's separate from the main CPU, so it's not draining much battery. And then if it thinks it's heard you say the magic words, then it will actually fire up the main, the main application processor, the main CPU, and it will run a larger model. But if you, Apple had a great article about how they do Siri on their phones, and they talk about running a very small sound recognition, speech recognition network on their DSP, which is very, very similar to this sort of device.
Oh, right, yeah, very low power.
Yes.
Interesting. Well, I can imagine, given the weight and the power and all, this could fit onto all kinds of mobile devices. I mean, mobile as in things that fly and swim and crawl and all the rest. Squirm, I don't know what else.
Well, I like the idea of just sticking this on as a sticker to, if you had a little bit of battery or a little, solar panel, you could basically just stick this to anything that you've already got.
That's a fascinating part too. You were describing before. There's only a few chips, but it seems like the bigger parts of it are actually the switches, the parts that would be somebody would try to touch. If you didn't have to do that, it could be a fairly flat
Exactly. So the main, you can see the sort of like the diamond-shaped chip. That's really the only sort of essential piece here. Everything else is like peripheral.
Wow.
So yeah, we've actually found we have some great little prototype boards from Ambic Micro, who are a startup doing extremely low power versions of these, and they actually have a coin battery circuit board. And the coin battery is like the largest piece, and the rest of the circuit board is just kind of, the chip in the middle, and then, so yeah, the power is really the, the limiting factor here. And the really nice thing about the neural networks is they're almost all compute. There's almost no memory access needed. They don't need a network radio.
Oh, interesting.
So it's something that's really, really cheap in terms of power usage. Is running neural networks, which is why they're such an interesting fit for these microcontrollers.
For these networks, can you give some scale, some references, comparatively, how large are they with the types of deep learning models that people are talking about at the conference?
Yeah, so they really, one of the things I really like about neural networks is they tend to scale down very, very gracefully. So what I'm working on at the moment to run on this little device is a neural network that has 20,000 parameters, and they're 8-bit each. So that works to be about 20 kilobytes in the flash, in the read-only. So I've got another like 44 kilobytes to play with for the rest of the program. And the model that I'm actually using is a very simple convolutional model. It has one convolutional layer. It takes in a 49 by 43 one-channel input image, and that input image is actually a spectrogram of the last 1 second of audio.
Oh.
So what it does is it runs an FFT for every sort of like 20 milliseconds through the audio data. And then out of that you get this, and then it sort of squashes the FFT down like 6 times. So, you have 256 buckets normally for the FFT, and it goes down to like, 43 or something like that.
So maybe for people who aren't as familiar with DSPs and signal processing, would it be fair to say that that's like having a histogram at time slices just sort of rolling across in the stream?
That's a great way of describing it. And a histogram showing what the different like frequencies that are present in like each time slice.
Right.
So if you have like, a very high frequency, you'll get like the bucket that's, high up, having a lot of, having a high value, and then otherwise like low values will fill up like the lower buckets. So what's interesting is you end up with this, if you look at it as an image, you end up with this kind of fingerprint of the noise, a fingerprint of the sound that's happening. And I have to admit, I was actually slightly disappointed because I was learning about how to do speech recognition and like how people do like audio recognition, and I thought I was going to be like learning all of these like crazy new techniques, and there are some crazy new techniques out there, but actually just doing image recognition, like turning your audio into a picture and then doing image recognition using the networks that you know and love is actually a really effective solution. So
Plus ça change.
Yes. But yeah, and what gets really interesting is you can actually look at using things like MobileNet as a very cut down MobileNet, like for slightly larger microcontrollers. If you can squish MobileNet into 250 kilobytes,
interesting,
that becomes quite an effective, simple image recognition network that you can use for audio recognition, but also potentially for things like gestures or sort of gaze tracking or other sort of tasks that you typically do with image recognition.
The distributed systems person in me immediately thinks too, is there a way to switch between audio and image? And then I sort of slap myself and go, no, it costs 50 cents. You just pile a few more on.
Well, I mean, the other nice thing too is that you can actually, because you're using the same neural network software to deal with both the image and the audio, it means that you have a really simple path to just like, oh, I want to pull in an image sensor. Okay, as long as I can just turn it into some numbers, I can feed into the network.
I'm curious too about your perspectives on audio. I think that a lot of people will, coming into the field, they'll hear the word audio being used, they'll think of speech to text or some sort of spoken, but audio is very oddly ubiquitous in our lives. It's like we can't turn off our hearing.
Yes.
And it has profound effects on us, even if we're asleep on a plane. The distribution of the noise affects things like taste and digestion.
Well, one of my favorite stories is I was talking to a large engineering firm, and they were talking about their factories, especially their factories in Germany, where every morning they say, there's almost every factory, there's usually a guy, usually named Hans, who walks around and he puts his hand and he listens to all of the machines, and each one he's like, oh, okay, that one's going to have to go offline for some servicing today, and then he's like, next one, he's like, oh, that one's going to be okay, but in a couple of weeks you're going to want to take it off. And every factory has one of these people who really understands the machines and listens to them, and they're usually going to be retiring over the next 5 years.
Yeah.
So if you can actually have something that's able to do that same kind of listening and predictive maintenance and just kind of understanding the world around you, it doesn't have to be just sound, it can be vibrations, it can be sort of any kind of time series signal, and just do that very human, intuitive, something doesn't sound right, out of this really noisy data. That's why I think, attaching neural networks to these cheap sensors and just being able to kind of do that kind of oh, I think something's a bit off here.
Interesting. I can imagine also for environmental changes and adaptation. Have you seen the thing recently where Finnair hired sound designers to work with their chefs?
No.
And the idea is you actually your taste flavor profiles change based on higher or low frequencies. And so one of the reasons why airline food tastes perhaps not the best. And you can change the soundtrack and actually change the flavor. I think there's a chocolate shop somewhere here in London that does tastings based on audio.
Oh, wow. Yeah, no, that's a fascinating idea, and being able to do that sort of sensor fusion as well, because one of the things that I ran across that I found really interesting was, even if you're doing speech recognition, voice recognition, you can really improve the voice recognition by taking in video at the same time.
Oh, interesting.
So there's a great paper that Google recently published about dealing with the cocktail party effect, which is where, if two or more people are talking at the same time, from a microphone's point of view, it just hears this babble, and it's very hard to pick out one individual voice. But it turns out if you have video, you can actually train a network to pull out all of the distinct voices from the audio track using the video as a sort of, looking at the lip movement and things like that. And I also think, one of the things I struggle with voice interfaces is once you have multiple devices, the whole idea of having a wake word becomes a lot more problematic. So if you can use image sensors to sort of tell, hey, I'm actually looking at the light switch, which I want to turn on. And then sort of combining image and audio and any other sensors and actually making more sense of the world.
Hand movement.
Yes, gestures.
Gestures with some voice.
You turn on.
Right. Oh, that's such a fascinating area of design, and just also so human, almost be able to dance with the machines.
Exactly. I've always loved that idea of sort of the Disney world, where you can actually talk to all these objects and they talk back, and you live in this happy little
Well, and alternatively, there's sort of the 2001 scenario of open that pod bay doors.
Yes.
Lip reading. Well, okay, so this is pure magic, but it's also very real. How are you accomplishing this?
So I'm getting a lot of help from people in the embedded world and in the microcontroller world, because I really am a complete newbie when it comes to working inside the kind of constraints. And yeah, I've had a lot of, you know, hardware sort of partners who've been incredibly helpful, sort of, you know, and incredibly patient, helping me figure out how to like program these. You know, we've got a great team working on this in TensorFlow. Like, this is actually something that a lot of us, you know, I should be clear, like, this is definitely not just me. Like, I've actually, you know, my teammates, Rocky and Andy especially, have been doing some amazing work, you know, getting these devices up and running, and, you know a lot more about it than I do. But yeah, we've really been diving into seeing how we can strip down and streamline TensorFlow so that you can take models that you've trained in the cloud and in Python, and then, like, you know, squeeze them into a really, you know, sort of the TensorFlow Lite framework, so that you can actually run then TensorFlow Lite on these devices, only using like a, you know, few tens of kilobytes of memory to run the program, and then you know, 20 kilobytes for a model. And it's still very early, and it's still very much a work in progress, but it's been really fascinating just seeing how well these very modern techniques kind of translate back to something that feels a lot like, you know, the computers I would program in the 80s. You know?
This is like circa 1978 or
yes.
something. Well, fascinating. You know, and there's no operating system per se on the board.
No, you can actually get operating systems, but this is actually, the way we run it is, you know, what they call bare metal, where, you know, you're just directly poking like memory locations to turn LEDs on, and you have complete control, mostly because, you know, there's so little room. You want to really make the most of, but we also, you know, we do work closely with like ARM, and they have their embed OS, and there's free RTOS, and there's all sorts of great sort of microcontroller OS solutions.
Right, very sophisticated.
But we're trying to basically make it so that TensorFlow is essentially just math. So if we can have as few dependencies as possible and be as portable as possible across as many OSs and devices, if we don't have to rely on OS services like this, we don't use any dynamic memory allocation, and we don't use any of the standard C library, and we don't use, you know, so there's a lot of stuff where we don't use floating point, and, you know, there's a whole bunch of stuff that we actually avoid so that we can be as fully portable to all of these different.
Well, I mean, it's interesting because when I hear the word TensorFlow, my immediate thought is some ginormous cluster running in the cloud, some huge data center, and just fantastic networking and all going on. And this is as far away as that is conceivable. Have there been learnings by working in the small? Have there been learnings that factored back into TensorFlow proper? Yeah,
and what I find really interesting is the more we strip it down, the more we get to sort of like the essentials of what's kind of required to do these networks.
Oh, fantastic.
So, you know, a good example of this is we've done a lot of work on the mobile and embedded team on running neural networks in 8-bit. So actually getting down to sort of, you know, instead of doing 32-bit float for all your values, actually do things as sort of 8-bit integers. Because a lot of these devices are much better at doing 8-bit math than 32-bit. But that actually translates back nicely to a lot of the server and the, you know, some of the cloud, like NVIDIA have some great TensorRT sort of 8-bit solutions. Intel have some great code for doing 8-bit stuff. So the work we've been doing on the training side to help train networks to run at 8-bit precision, because they need to be sort of modified so that they can handle the lack of precision, has then sort of fed back into some of the, you know, the cloud sort of deployment and the cloud training stuff. So there's been a lot of, you know, we're still very much part of the main TensorFlow team, and there's, you know, there's a lot of really productive back and forth that happens when you're running all the way from tiny chips like these up to sort of crazy, you know, TPU clusters.
Yeah, exactly. I was thinking like large ensembles of TPUs. Well, another question I have is sort of looking ahead and seeing the future through your eyes. I'm really curious because it's Coming from O'Reilly, what we're hearing a lot on the ground that I don't think is fully appreciated as much in the industry is just how dramatic the hardware changes are that are coming down the pipe and what the consequence is on AI, data in general. It seems like this is a game changer to get a device like this out in the real world.
Well, the nice thing is that there are already like 10 billion of devices like this being sold every year, and more.
Right.
More and more every year. There's like tens of billions of these out there already. So the hardware is kind of sitting there waiting for us
to... Ominous.
Yes, no, in a great way. Like
yeah, exactly.
Waiting for us like a birthday present.
It's an opportunity.
Yes. Waiting for us to actually get these things running on there. So, and there is a lot of really exciting new hardware coming out too in this world, which is going to make things even better. But even if we can just run with what's out there already, I think there's some really fascinating ways that we can improve sort of products and improve people's lives. And then if the hardware gets even better, then you know, we can do even more. So
it strikes me, I remember a conversation right around the .com crash. I mean, showing my age.
No, I was there.
But you know, I remember a conversation and somebody was saying this rather striking thing about a lot of dark web or dark fiber that was out in the world.
Oh, yeah.
And how it was being bought up and possibly put to use, and other people were arguing and saying, well, there's really no need to transfer that much data. You know, I mean, how on earth did somebody really leverage that in a business use case?
Yeah.
And here we've got a similar kind of thing with a lot of, I won't say dark hardware, but I mean, it's latent.
It's latent compute that's kind of not doing anything right now and could be doing some really useful stuff. So,
oh, fantastic. And also just, I mean, going back to the physics of edge and cloud and IoT and all that, it's a hard problem to take a lot of data and send it up to the cloud and bring it back down and make any kind of judgment within microseconds.
Yeah. The latency is a really important use case for doing things on like mobile phones and on the edge. But the other thing that we find is if you look at, you know, something like Siri or OK Google, it's essential that you have something running on the device to wake the device up. But then it actually sends a lot more traffic to the cloud. So it's not like these are in, you know, the cloud and the edge are in competition. We see like the more intelligence you get at the edge, the more chance you have to do things at the cloud level as well.
Oh, to really use it.
Yeah, to really use it. Well, to use it efficiently, but even like if you think about it, you couldn't have launched something like Siri without having on-device and cloud.
Right, yeah.
You know, capability. So if the on-device capability hadn't existed, the cloud capability would never have been like, you know, used. So
interesting. So I mean, what that portends is that there's a lot more of these kinds of applications we haven't envisioned yet.
Yes.
And also design patterns that...
Yeah, interact, like now that we have the ability to recognize gestures and to recognize, you know, starting to be able to do a much better job recognizing speech and, you know, gaze and all of these things, like how can you sort of interact with objects in the world in a very natural way where, you know, if there was another person sitting across from you, they would know what you were talking about. Right. So why, you know, why doesn't your toaster?
Fantastic. Thank you very much, Pete. I really appreciate it.